All right, pretty easy and short section to start off here. We're going to find limits graphically and numerically. So essentially, we'll give you a graph, and you got to decide whether it has a limit or not. If it does have a limit, you'll tell me that answer. If it doesn't have a limit, you'll tell me why it does not have a limit. So the notation that is read the limit as x approaches 4 of f of x. Sometimes we'll use that function notation. Sometimes we'll use the actual function right there. But what that means, really important, what this means, as your x's get closer and closer to that 4 number from both the left side and the right side, you're asking yourself the very important question, what are our y values approaching? What are our y values getting close to? I don't care what the y value is. It might be the same, it might not, but a limit and a y value, two different things, okay? I wanna know what are my y values getting close to? That's it. That's what a limit is graphically. So as we look at these two graphs, I'm gonna ask two things. I'm gonna ask what's the limit as x approaches 4 of those two graphs. I'm also gonna ask this notation you already know from your Algebra 2 days is just what that y value is, okay? So let's just do the limit part first. When I ask you what's the limit as x approaches 4, that's x equals 4. That's your vertical barrier. So what you could do, you don't have to do this, but maybe at the beginning it might help some people. But that's your vertical barrier, okay? That's your x equals 4 line right there. So what you're asking yourself is as I approach that vertical barrier from the left-hand side and from the right-hand side, so we're pretending like we're a little stick figure guy right here. And he's going to go up that hill. He's only allowed to travel along that curve, that red curve. He's going to go up that hill and get closer and closer to that vertical barrier, right? And then he's got a friend he's going to meet for like a picnic at that picnic table down there. And then I guess she needs some arms there. So then she's going to come downhill. And then what you're doing is what are the y values getting closer? So as he goes up that hill and gets closer and closer to that vertical wall, notice that his y value right here might be like at a 5.4 and then a 5.8 and a 5.9. And right here, when he's right next to that vertical wall, it's like a 5.99999, right? That's what we're looking at. And then as she's coming down that hill, when she's right here, her y value is like at a 6.1. And then it gets a little closer. It goes 6.01, 6.000001 when she's right to the right of that, okay? So both of those people, their y values are getting closer and closer to that. I got 5.999 and 6.001. Both those y values are getting closer and closer to 6. So that's what that limit answer is. Also, this notation is algebra 2. It just means when your x is equal to 4, what is our y value equal to? That means what is the closed dot? So you have a closed dot right there. You got the coordinate 4, 6. That's just what is that y value. Notice that they happen to be the same thing on this one. They don't have to be the same thing. As you look at this next graph, I think you probably see where this is leading. When I do the limit as x approaches 4, if we draw on the vertical barrier there, and as you're that stick figure guy coming up that hill, approaching that vertical barrier, from the left-hand side, again, you're getting like 5.9, 5.9999999. You're getting closer and closer to 6 from the left. And then your friend coming down that hill, trying to meet you at that picnic table right there. When she gets closer to that vertical barrier, her y values are like a 6.1, 6.0001. So notice how your y values keep getting closer and closer to 6 as you go toward that vertical barrier, and your y values keep getting closer and closer to 6 as you go towards the vertical barrier from both sides. That limit answer is still equal to 6. So that one point, where the point is at itself, has nothing to do with the limit. The limit is strictly to the left and to the right of that picnic table, of that meeting point where those friends want to meet. That's what that limit is. As you approach that vertical barrier or that picnic table, you want to know what are your y values doing? What are your y values approaching? Now, if I ask what is f of 4, that means when my x equals 4, what's the y value? So that y value, that's equal to 10. And see how they don't have to be the same thing. They could be the same thing when you got a nice, smooth, continuous graph like that. But if you got a jump or a break or an asymptote or something like that, they don't have to be the same thing. Even if I remove that dot entirely, the limit answer doesn't change. That limit would still be 6 because the left and the right are still not changing and getting closer and closer to 6. If I take this dot away, though, then that changes that 10. That 10 becomes an undefined, all right? There's no point on your graph when the x is equal to 4, but the limit is still 6, whether you have a point there or not. So just kind of keep that in mind. Even if I take this point away, right, we're going to do a lot of normal functions with limits, and bunch of different techniques here. If you plug into an equate like an expression and you get 0 in the denominator of a fraction, that just means your function doesn't exist there. It means you got a hole in your graph, you got a vertical asymptote, but it's entirely possible that you still have a limit, because a limit still can be the left and the right hand side. It still can equal something there. So what I want you to do now is just kind of pause the video and just jot down these few graphs in your notes, and then we'll go through the answers, and then we'll do a few more there, okay? All right, so assuming you got those graphs down, what we want to do now, just tell me what the answer is. That's it. And then a couple weird things happen on this that we'll talk about and make sure we're real thorough here. But here I want the limit as x approaches 2 of the h of x. So there is already my vertical barrier. So again, you're like that stick figure guy. And what you're doing, you're only allowed to travel on here. So from the left-hand side, if I'm going up that red curve on the left, and I want to get closer and closer to that green vertical asymptote, as I go up that curve, I'm asking, what are my y values doing? As I'm going up, they keep going up, 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 so that answer is infinity. Same thing if you're coming from the right-hand side, and you're getting closer to that green vertical barrier, that x equals 2 line, you're also going up, up, up. You ask yourself that question, what are my y values doing? What are my y values getting close to? What are my y values approaching? Both sides, you're going up to the skies, you're going up to infinity, a positive infinity. So that's your answer. If they are both going downward to a negative infinity would be your answer. Let's talk about what happens here. See, from the left-hand side, you're going up to a positive infinity like we talked about here, but the right-hand side, you're doing something different. You're going down to a negative infinity. You're not going to put a positive or negative infinity. It's not that, all right? If you can't give me one single answer for a limit, that answer does not exist, all right? We can abbreviate that as DNE. You either can put does not exist, or you can put no limit. Those are your two options, not undefined, not anything else. It does not exist or no limit. Those are your two answers. Now, for the whole entire year, if a limit doesn't exist, you're going to tell me why, always. It's the whole year, right? So does not exist. The reason this limit doesn't exist is because, very common reason, the left-handed limit is not equal to the right-handed limit. So you can abbreviate it like that. So that's what we would need on that problem for a homework, for a test. That's what we want to have down right there, okay? Because the left-hand side is a positive infinity, the right-hand side is a negative infinity. They're not equal to each other like this one, so I can't give me a single number for that. So we're going to put D and E does not exist, left-hand limit not equal to the right-handed limit. This next one is called a piecewise function. This is a step function. This is actually something called a greatest integer function, which we may learn that later, a little later in the year. But if I say the limit as x approaches 2, so x approaches 2, realize your vertical barrier is right here. And see, if you're only allowed to travel on a step, see, like when you approach that, when you travel along that green step and you get closer to that red vertical barrier from the left-hand side, see how my y values are approaching 1, or they're all equal to 1. And then when you're from the right-hand side, though, your y values are up here, you're approaching 2. So that limit is not the same, all right? If you're two friends trying to converge into a picnic table, guess where you're at? You're at two different picnic tables right there, okay? So all you're concerned about is what's going on to the very left, what's going on to the very right, and those must be the same for that limit to exist there. So this answer is another DNE, for the same reason the left-handed limit is not equal to the right-handed limit. This number is pretty important. You have to be careful what you're looking at. If I change that to a 2.5, guess where 2.5 is at? 2.5 is right here in between 2 and 3. So that's smack dab in the middle right there. That's our vertical barrier. And if you can look at the very left of it and the very right of it, you are approaching the same thing, all right? You are approaching the y value of 2 for both of those. So that answer is actually existing as 2. So you got to pay attention to where that vertical barrier is at and get that right answer there. So let's do a little recap of what your typical limit answers will look like. So you need to make sure you're getting the right stuff there. A lot of times you're just going to get a single number, like we did in the first couple of examples, or you're still going to get a single number, but it's not a finite number. So you can get infinity or a negative infinity as your answer, like we saw here, here, and then we saw right there, right? We saw a single number, infinity, or negative infinity. Or if you can't get a single number, and there would be a couple other reasons here, but if you can't get those, then your answer is going to be does not exist. Or you could say no limit, right? But, you know, or no limit. But a lot of times people just prefer to put does not exist. And then, like I said, the whole year, what I need you to do, anytime a limit does not exist, tell me why. And that's going to be like for chapter 3 when we revisit limits. That's going to be in chapter 8 when we revisit limits. And so that's what we want to talk about there. All right. So you want to pause the video for a brief second. And then what I want you to do is just jot down those couple of graphs. And then we're going to draw this graph together. And then here we're going to talk about the oscillating nature and what happens with those limits right there. If I give you a sine graph and I ask you what's the limit as x approaches infinity, now this is going to be true for a sine graph or a cosine graph. The limit as x approaches infinity. X approaches infinity means as my x's get larger and larger. So as I go out to the right along that x-axis, I want to know what are my y values doing? What are my y values approaching? Now we know on a sine graph that just forever fluctuates in between 1 and -1. All right. And remember what you can't put there. You can't put plus or minus 1. You can't give me a range of values in between -1 and 1. I'm not asking for the range of this thing or a domain of this thing. Forget all that. I'm asking for the limit. What are your y values getting close to as you go farther out to the right as you approach infinity? And remember, since you can't tell me a single number right there, you got to put does not exist. So there's our answer for that one. And then it's not that the left-hand limit is not equal to the right-hand limit. That doesn't make any sense. All right, here's the second reason why a limit doesn't exist is you simply just put it doesn't approach a single number. And we'll recap the reasons why a limit doesn't exist in a minute here. But so far, that's the second one. Now, just because you see a sine graph or a cosine graph, it doesn't mean that's always going to be the answer. If you got to look at what you're approaching. If I do a limit as x approaches power 4, guess where power 4 is at? That's right here. And if you're looking at that as your vertical barrier from the left side and the right-hand side, you actually are approaching the same thing, all right? And it's going to turn out that that's just like the sine of power 4, which is going to be the square root of 2 over 2 right there. This next one also oscillates. But notice as if I do the limit as x approaches infinity of this g of x, notice as I approach infinity, as I go farther out to the right on the x-axis here, this graph just keeps getting smaller and smaller and smaller, and this actually does narrow down. So this one didn't narrow down, it just kept going between 1 and -1, 1 and -1. This one actually narrows down for us, keeps getting smaller and smaller. It does approach that single number, it keeps getting closer and closer to 0, and then you're good. All right, just like on the irrational functions, when you have an asymptote and you keep getting closer and closer to something, that's technically the definition of a horizontal asymptote. What's that limit as x approaches infinity? But we'll do that stuff in a little bit of a later chapter. All right, one more oscillating graph we got to talk about here. All right, let's kind of draw this together. All right, we're going to start off just nice and smooth, up and down motion there, and then in the middle, they're always going to have this this crazy heart attack there, all right, and then just shake it off, shake it off, shake it off. And then you're gonna go about your way, right? So there's just this mass chaos going on in the middle of that graph. And you might think that's like a crazy equation. I think the equation looks pretty darn elementary there. It's like tangent of 1 over x or something like that. It's just a basic trig function. But what I want to know is what's the limit, if I call this g of x again, I want to know what's the limit as x approaches 0 of g of x. Now we could delve deeper in this in the future. In the future, we're going to work with the graphing calculator a little bit. We'll graph these things, and when we graph them, and if we make XY charts and we type in like 0.1 and -0.1 and 0.2 and -0.2 and then 0.0001, our y values when we make the XY chart are all over the place. It's just jumping all over the place, doing that massive heart attack stuff right there. So just like this one, you're not able to get a single number for it. It's just mass chaos going on. Now, you could have it oscillating, but if it oscillates like that crazily, then you're not going to be able to narrow that down. So this is another reason that doesn't exist. So we're going to put does not exist for that. And then the reason that we use is it simply oscillates too rapidly. Oscillates too rapidly. Now, let's recap the reasons why a limit doesn't exist. I mean, they're all right there, so I just wrote them down for you. What you're going to use probably most of the time is this first one. That's the most common reason why a limit doesn't exist, is the left-hand limit is not equal to the right-handed limit. But you just saw this second reason right here, it doesn't approach a single number, and then you saw this one right here, where it oscillates too rapidly. Okay, so there are your 3 reasons. And even when we revisit limits later on, those are still going to be your only 3 reasons why a limit does not exist. So we got those down automatically. Here's a common mistake. Sometimes people see an oscillating graph. Sometimes they give me this. They'll say it doesn't exist, but then they just put oscillates. If you write down oscillates without the too rapidly after that, that is wrong, right? Because look, that's an oscillating graph. We got an answer for that. That's an oscillating graph. We got an answer for that. So for you to say it doesn't exist because it oscillates, we can get answers for an oscillating graph. That's just false reasoning. So you got to make sure that you use these 3 reasons right there. It's all about learning. Sometimes I'll be pretty straightforward with some of these things. Sometimes I am going to be picky about some of these things, because when we do this AP review and this AP test, we need to make sure we justify our answers properly. It's really, really important that we always justify stuff, and we'll make sure we're showing our work the right way from the get-go, because the AP graders are more concerned with how you got the answer and what your thinking was going on in your head, and if you're justifying using proper reasonings for things versus just the answer by itself right there, right? And so we'll get you plenty of exposure to all those things. One more thing in this section here is the numeric approach. So graphical approach, you look at the graph, you get the answer for the limit. And then there are things out there where there are no algebraic techniques. We're going to learn a lot of methods of how to find a limit algebraically. Even when we learn a lot of different techniques in the future, there's going to be certain things out there that there is not an algebraic technique for. And so we got to rely on what we just talked about in this video, the graph. And sometimes we don't want to graph this thing. Like, I don't want to graph every single function right there, especially if I don't know what that graph looks like, or I don't have a graphic calculator. I'm not allowed to use a graphic calculator. So what we can do is make an XY chart. We're going to pretend we don't know any algebra on this and we haven't learned any of that stuff yet. All right, so if we make an XY chart, what you need to do is make 2 XY charts, and you need to approach one from both sides. So if you're thinking, hey, here's a 1 on the number line, I needed to approach it from the left-hand side. That's like the 99-cent side. So you're talking like 0.9, 0.99, and 0.999, right? So you started to the left a little bit, and then you gradually got closer to the number 1. And then from this side, it's like the dollar and a penny side. So you're talking like 1.1, 1.01, 1.001. And the reason I do that gradually, I started to the right a little bit and then gradually get closer, because when we do infinity limits later on, like, we'll see the answers go from like 10 to 200 to 2000, and that'll be our work and our justification for, hey, that thing is shooting off to infinity, right? So we develop some good habits and do these things the right way. So when we get to them later on, we're already going to know how to do it. And then all you've got to do is you're going to take these numbers here and you're going to plug those in place for X and plug that into the calculator. So be careful when you're plugging into the calculator. Make sure that you put the top and the bottom in their own parentheses there. And I'm just going to write down what these numbers are, because I'm sure you guys can handle plugging an easy number in the calculator there. So just take a second and jot these down. And then we'll show you how to get your answer. All right, now see how as we're getting closer to that 1, that answer looks like it's going to be 0.5. And here, as we're getting closer to that 1, that answer also looks like it's going to be 0.5. So the left-hand limit and the right-hand limit are both the same thing. So 0.5 and 1/2, that's going to be our answer right there. All right, now when you do a graph or an XY chart like that, that's like an estimated answer. All right, that actually ends up being the exact answer on that one. But think about if your decimal answer, think about if the exact answer ended up being like radical 7/18. There's no way that you're going to recognize what the decimal answer is for radical 7/18, right? So we're going to learn better techniques other than just making an XY chart, where we're going to be able to get the exact answer without doing all those calculations right there, okay? And it'll give us the exact answer. So when we learn those, we need to use those. And then when all else fails, then we go to the XY chart if we need to, go to the graph if we need to. So as we're doing our homework, we give you a couple where you just need to make a couple XY charts, or even set you up at the table and you just got to fill it in. You should show that work on your homework there. If I give you trig, Make sure your calculator is in radian mode, otherwise you're not going to get the right answers right there. We'll pretty much use nothing but radian mode in this calculus class there, so you could set it in radian mode and leave it like that the entire year. And then the rest of the assignment, it just gives you some graphs like here, and it just asks you for the answers. So it's not like there's any work to show on that. You just kind of get those answers, but if it doesn't exist, then you're going to tell me why, and then you can let me know if you got some questions.